Everyone, thanks for joining and welcome to today's online course. I'm Ellie from the PTI and I'm just going to run through some quick housekeeping with you before I let Alison and Charlie lead today's course. And now I'll pass over to Alison and Charlie. So thank you so much for joining and I hope that you enjoy the course.
Thank you so much, Ellie. Hello, everybody. It's really good to be here today. If you want to say a quick hello in the chat and just briefly introduce yourselves, you're very welcome to do so. I want to tell you a little bit about what Charlie and I have got planned for you over the next just under an hour and a half. We are thinking today about three-dimensional thinking. And we thought quite a lot about what to call the session for the particular tasks we want to share with you today. Because on the NRICH website, 3D thinking gets broken up into some slightly different places, and we'll show you a little bit of this later on when we're looking at how to navigate the mapping document. But some of these problems are from the three-dimensional shapes part of the mapping document, and some of them are from the surface area and volume collection of problems, because those are the places where 3D thinking really seems to crop up, just plain thinking about three-dimensional shapes, but then specifically thinking about calculating things with three-dimensional shapes, calculating surface area, calculating volume. And this is something where I always have a lot of imposter syndrome in talking about it. And it's one of the things that I'm not as confident at teaching, simply because I find it really hard to visualize things in 3 dimensions. I find visualization hard generally, but picturing things in 3D, I just find almost impossible. So I've had to come up with lots of strategies to help me when I'm answering questions about 3-dimensional shape. And I think that is true for some of the students that we teach, but then others seem to have incredibly detailed and rich models in their minds of how to work in 3 dimensions. So it can be one of those topics where some people just get things instantly and other people really struggle with it. And so, as with anything like that, I think having lots and lots of descriptions, lots of opportunities for students to talk about how they see a problem, lots of collaboration so that they can feed off each other, I think it becomes more important in this particular topic than it even is just in learning mathematics generally. And I also think it's quite important to make sure there is stuff to support learning. And so, for example, when I'm trying to work in 3 dimensions, I often use some isometric dotty paper so that I can start sketching out little cubes and so on. Sometimes I like to get some multi-link or some Lego bricks to actually build 3-dimensional structures to be able to start perceiving them. And quite often I use GeoGebra, which has a 3D drawing part to it as well, to create 3D models on the computer to use it. So those are ideas to bear in mind at the back of your mind as we're going through some problems today. But to start off with, Charlie, you've not said anything yet because I've launched straight into an introduction, and you're actually going to be introducing our first task. So why don't you say hello to everybody and then tell us what we're going to be doing to start off with.
Okay, hello to everybody, and glad to be working with you. I'm going to share my screen straight away, I think. Let me just check. I might have to reorientate it. Okay, so I've got a square sheet of paper. Hopefully you can see that. 20 centimeter by 20 centimeter. And the problem that we're going to start off with is called Cuboid Challenge. So I'm going to turn this round to show you what I've prepared in advance. And the idea is that we're going to cut out squares out of the corners. So I've drawn some squares already that I've prepared earlier, and I'm going to cut them out, and that will give me the chance of making a cuboid without a lid, a box without a lid. And one question we could ask students is, will the volume of our cuboid be the same, irrespective of the size of squares that I cut? So if I cut small squares, I will have a large base, but it won't be very tall. If I cut big squares, the base will be smaller, but the height will be taller. The idea is, so will it make any difference to the volume? And if it is going to make a difference, then, so here's my box without a lid made. If it is going to make a difference, can we say something about how the volume is going to increase or decrease? When might it be at its largest? So starting with a 20 by 20 centimeter square sheet of paper, the idea is to cut out corners, and if we were working in a classroom together, you'd have the chance to, we'd give you some square paper, we'd give you scissors, and you might have a go at this. And if we were with younger students, we would definitely do that. But we're not in a classroom, and I imagine you can picture what this looks like and what the volume, how to work out the volume of the cuboid. So what we'd like to ask you to do as your first challenge is to decide on what size cut you're going to make. I think we'll stick to whole numbers. So you could have cut, I could have cut a 1 by 1 centimeter square, 2 by 2, 3 by 3, 4 by 4, anything up to almost 10 by 10. But we could have cut 9 by 9 squares. And it'd be quite nice to have a variety of results in the chat. So in the chat, we'd like you to just write down what size square you imagine cutting out and what you think the volume will be of your cuboid. And then we'll have a look at the results, and we'll talk a little bit about the results that we get and think about how we would do this with the classroom. Is there anything I need to add, Alison?
I don't think so. So what you want me to do is you want me to choose, well, you want all of us to choose the size of square that we're going to cut out in the corners. And then we're not actually going to cut it out, but we're going to work out what the dimensions of our box would be. And then do you want us to post in the chat to say the size of square that we cut out from our 20 by 20 and the volume that we got at the end of it?
I think so. I'm not sure there's any need to write all 3 dimensions.
Okay.
People particularly want to.
Okay. Well, let's take a couple of minutes then. I'm gonna have a go. I have cut a piece of paper out because I'm not very good at visualizing. But yes, I'm going to work with my piece of paper here. And then I might also do a little bit of sketching of it, but then we can all post in the chat once we've done an example to say what size of square we cut out and what volume our completed open box had.
So Maddie's already contributed, and Maddie, we're very happy for you to contribute some more. It might be quite nice if by the end we've got the volume for the 1 by 1, the 2 by 2, the 3 by 3, all the way to the 9 by 9.
And if anybody else is also working on the 3 by 3, you can check Maddie's answer and make sure you agree with her. So Laura and Rico have both done 324 from a 1 by 1 square. Lovely. Okay, we've had 588 confirmed for the 3 by 3, and we've got 512 for the 2 by 2. I said I was going to do one, wasn't I? Guess I ought to do one.
I've got the results, and everything that's appearing on this chat seems correct, which might not always happen in the classroom.
I was just about to put that one in. 9 by 9 gives volume of 36. I think we've done most of them now, haven't we? Nobody's done 8 by 8. Nobody's done 7 by 7. Let's give everybody another minute or so in case anyone wants to do one more. $128 for the 8 by 8.
So it looks, Alison, like, well, the volumes are different, and it seems they seem to grow and then they come down again.
So Demelza's gone away from using whole numbers and done 10/3, which is 3 1/3 by 3 1/3, and got a volume of 593.
Maybe I'll put on the screen the whole number results that I've got, and why perhaps Demelza has gone for something between 3 and 4. So on the left,
I suspected you might have done, Demelza. I've just seen your comment about how you worked that out.
But for younger students, they might see that the cuts of 2, 3, 4, 5 of 5 give us volumes of 500 and a bit more, and the maximum seems to be close to 3 and 4, and so students might work with calculators, or they might work out a formula. I was thinking in terms of my 20 by 20 and cutting out X by X's. And so I was going to have a base which was 20 minus 2x by 20 minus 2x, and the height was going to be x. And students could use that kind of formula. And I know that Alison's been working using the formula, so I'm going to stop sharing my screen so she can show you what she's been doing.
Okay, so I used the formula to create this. Can everyone see my GeoGebra screen now?
I can.
I'll assume everyone can then. So I created this in GeoGebra using the 3D graphics because I wanted to be able to visualize what happened. So I've got a slider on the left, which as it increases is going to cut out a bigger square so that this then folds up into a cuboid. So as A increases from 0 to 1, I've now got this, if I cut out a 1 by 1 square at each corner, and so I've got that 18 by 18 cuboid with height of 1, and so that's giving me a value of 324. And what's happening on the box on the left is that the graph is showing the volume of the cuboid for each value of A that I plot. And so I can continue on up to 2, up to 3. And this is nice because I'm starting to show the in-between values as well to students. So I might have started just by talking about whole number values, but this makes us move to the in-between values. And as Charlie says, you might use calculators to put some values into the formula. Trial and improvement doesn't come up on a lot of exam board syllabuses for GCSE now, but numerical methods at A level certainly means that having done some trial and improvement based thinking is really useful. And actually, I think just from the point of view of a skill for real life, being able to do a numerical approximation to find this maximum value and saying, well, it's somewhere between 3 and 4, let's try 3.5. And then carrying on, going through that. And it's also a good opportunity to show how you can use spreadsheets to put a formula in and very quickly do it. This particular GeoGebra is not online yet. I've just seen the message in the chat. I am going to make it available after today's session. I need to do a little bit of tidying up on things and upload them, but there will be an email coming out to you in the next couple of days. And one of the things that Charlie will confirm I put on my to-do list today is to upload it to my website so that I can share it. So I'm going to carry on moving the slider across, and then you can see that as you get down towards 10, it's tailing off again. And I think showing this cuboid growing and shrinking again and being able to see it side by side with how the volume changes and how the shape changes, I think this is quite nice for some of the developing intuition, which is the bit that I wish I had started to develop earlier, because you can see how a small change in what you cut out is increasing the volume and then decreasing it again. So you go from these sort of very, very flat cuboids where they've got hardly any height to them, so the volume is quite small. Then at the other end we've got these very, very tall thin cuboids, so they're quite small. But then in between we're sort of using our dimensions the most efficiently to be able to get the best example of a cuboid. And I've also got a GeoGebra window here, which shows the graph. This is for a paper length of 20, and behind the scenes, it's done exactly what Demelza has done and done a little bit of calculation, a bit of differentiation to find that maximum point. And then this allows us to explore a slightly different question, which is to say, if instead of starting with a 20 by 20 square, what if I'd started with other sides of square? So let me take this back. So that instead of a 20 by 20, what would you like me to show, Charlie?
I'd quite like you to show me something that's a multiple of 6.
Okay, well, let's go to 18 then. Okay.
3 1/3 is the proportion. What fraction of the 20 may be consistent, whatever the shape, the size of the sheet.
So here we are then, we've got 18 by 18, and so the maximum amount that we can cut would be 9, and that takes us back down to 0 again. Nice, interesting opportunity here to discuss that when you plot a graph, you're going to get solutions and things going on that might not apply to the real world problem. So a good bit of mathematical modelling here, because of course, going beyond 9 on this graph would mean that I would be cutting off like a negative amount of paper to make my box. And so then it starts to grow again, but that doesn't make sense in the real world. So a nice conversation to be had about what the graph means beyond the limits. But yes, if I set the paper to length to 18 instead, it looks like my maximum point is at exactly 3 rather than, what was it we got before, 3 1/3. So your conjecture, Charlie, is that if I go to any multiple of 6, I'm going to get a whole number.
Yes. So
So-
if the paper length is 30, I think it's going to be 5. There we are.
Yeah. So again,
Could we look again at your first file?
yeah.
I'm curious about the shape of the cuboid when the cut is at about 3 1/3.
So
My
there's
intuition, you talked about intuition, and my intuition was possibly that I should be looking for a cube, but I don't think it is a cube, is it?
no. And so then again, that's something where when you've got these smart kids who are good at visualizing like Charlie, and they have an instinct of what they're gonna try, and then sometimes it can be surprising. So this reminds me a little bit of some problems, analogous problems in 2 dimensions, where you're thinking about how to maximize an area given a particular perimeter. And I think there's a problem on NRICH called Fence It, which is about if you're building a fence, but instead of just freely building a fence, you're building it up against a wall. And I think a very similar thing happens in that you might expect that a square would maximize it, but because you've got this fixed wall that you're working from, then it's actually not a square, it's a specific ratio of rectangle that maximizes the area.
I think it's half a square, isn't it?
Yeah, I think so.
You've got a picture, imagine the other half being on the other side of the wall.
Yes.
And that sort of makes sense because you want to make as much use of the wall as possible. Here, it's less clear to me why we end up with something which is 3 1/3 by presumably something like 12 2/3 by 12 2, or no, maybe 13. And anyway, I can't
Yeah.
do the arithmetic.
Yeah. I think I don't have a lot of intuition for this, but I think it's because you're taking away X by X at every corner, that X sort of counts twice. And so it's because of the way that we are constructing the box by cutting out squares from the corner, means that if you tried to make a cube, then you'd be wasting some of your cut.
Okay.
But
what I like about this problem, Alison, is that you could imagine doing this with primary school children and giving them a 20 by 20, a sheet of 20 by 20 centimeter square paper, and they could be doing this with multi-link. They could be cutting 1 by 1s, they could be then cutting 2 by 2s and so on, and they could just be counting the cubes, or they could be making the cuboids, sticking the flaps with sellotape and working out the volume. Then at secondary, we would work like we've been working, where we could picture what the dimensions are going to be. Then at
and it definitely goes up into Key Stage 5, because you can start doing the calculus to find the minimum point. And you can even, I've got another file just here where you can say, if I changed the width and the length of the paper. So if I said I started with like a 60 by 40 rectangle and cut the corners out to make a cuboid, where would the maximum point be then? So you're now working with 2 different dimensions and try and work out what's going on there. So it's got a lot of upward growth to it. It's a nice example of a low threshold, high ceiling task, I think. I've stopped sharing because I can't remember what we're doing next, and I can't look at my screen while I'm screen sharing. Is there anything else you want to say about Cuboid Challenge before I set you your next problem?
Yes, we sort of jumped from lower secondary to sort of post-16, but somewhere in between, we might get students using spreadsheets, writing out the formula like that, or drawing using it to draw graphs a bit, like you've done.
I do have one more thing to say, which is that you cut out the 4 corners. I don't know about everybody else, but I always found that when I was a classroom teacher, my scissors would go walkabout. And so finding ways to do tasks that didn't involve getting scissors out was always an advantage. I don't know how well you can see my screen, but what I've done here is I've taken my lines and I've just folded each one over and then made a little triangle shape at the corner. And so instead of cutting out the square in the corner, you can just sort of paper clip it out of the way to make the box instead. And so that's an alternative that doesn't have to use scissors.
And presumably you could also challenge students to cut the 4 squares with just one cut of their scissors.
You could, but then I think you'd be trying to do too much all in one lesson, to be honest. So
it's the kind of thing that Katie Steckles does, and she can cut every letter of the alphabet, I think, with just one cut of her scissors.
She can.
Well, each letter, not all the letters of the alphabet, but each one in turn.
Each one in turn, yes. Okay, so I think the nice thing about Cuboid Challenge is it's a good opportunity to start thinking about how volume can change starting from, so we haven't kept the surface area the same, but we've started from a particular area and then made shape by cutting out. And so you could look at the surface areas of these shapes as well fairly easily, because you've got rectangles cut out of squared paper, and you can start saying, well, I need to put a lid on it to make the complete surface area. But this interplay between surface area and volume is a really interesting thing to look at. And so for the next problem, I'm going to give you a challenge, Charlie, and I want you to talk through your thinking as you solve it. So I'm thinking of a cuboid, and
can I just stop you a second? I think I might share my screen and go drawing or writing.
Okay, yeah, that's fine. I'm just going to have a drink of my this is iced tea, by the way, everybody. It's not beer. It's very good iced tea as well. Everything okay, Charlie? Oh, there we are. Yes, I can see your visualizer now. Okay, so yeah, I'm thinking of a cuboid, and all of the side lengths of my cuboid are different, just to make things a little bit easier for one of us.
Okay.
And what I'm going to do is I'm going to tell you the 3 different areas of faces that you get. So I'm not going to tell you the surface area of the whole thing, but I am just going to tell you the 3 areas of the 3 faces that you can see in your drawing. So one of them is 15 centimeters squared.
Are you allowed to tell me whether that's the smallest or not?
Well, I'll just tell you all 3, and then you can decide where you want to write them on your diagram. So 15, 24, and 40 are the 3 areas. And what I want to know is whether that gives you enough information for you to be able to work out the volume of my cuboid. So everybody else can be having a think about this as well. But Charlie, I would particularly like you to talk me through what your thinking is as you try and solve this challenge.
Okay, so I'm not going to start thinking about the 24. It's got too many factors. And 40 has got quite a few. I'm going to start with the 15. So I suppose it could be 1 times 15 by or 3 by 5, assuming you've chosen whole numbers for the edges. So I'm going to assume that because it's the end of the day and it's hot, you will have chosen something less. So I'm thinking that it might be 3 by 5, and I'm thinking also that the surface area of this one is a multiple of 5, and the surface area of the top face is a multiple of 5. So I'm tempted to, let me just redraw this, just assume it's the same cuboid. I'm tempted to start by thinking that that might be 5, that edge there, this edge here. And if that is the case, then that's 5 by 3, which gives me the 15. and if the height is 3, and we know the surface area of one of the vertical faces is 24, then this must be 8. So 3 by 8 gives me the 24. 3 by 5 is going to give me the 15. And I now just need to check the 40. And that works because I've got 5 by 8 is 40. And you wanted the volume, didn't you?
Yes, please.
So the volume is going to be, well, I've got a base of 5 by 8. So I can fit 40 cubes along on the bottom face. And I've got a height of 3. So I can have 3 layers of 40, and 3 layers of 40 is 120. And if we assume we're working in centimeters throughout, and I label everything from the beginning, which I didn't do, then I'm going to have a volume of 120 cubic centimeters.
Correct.
Oh, good.
So what I'd like you to do now, or what I'd like everybody to do, I'd like everybody to choose a length, width and height of their own, but keep it very secret, and then work out the 3 different volumes that you get. Sorry, the 3 different areas that you get. And then if people could post their 3 areas in the chat, and then choose somebody else's 3 areas to work on to see if you can find their volume. And Charlie, can you set a challenge for me, please, just so I can explain what I mean by it. So can you quickly come up with a length, width and height that you're going to keep secret, and then tell me the 3 areas that you get from them?
Okay, and what I might do is I'll post it in the chat, shall I? So that everybody can see it.
Okay.
Okay, so surface areas, I'm going to give you 12, 36, 48.
Okay, am I allowed to use a calculator? It's the end of the day, please.
Okay, so I've posted it, everyone can see it.
Okay.
The new surface area is 12, 36, 48. Can you work out the volume?
Okay, so can I use a calculator?
Okay.
Because I mean, I'm thinking that 12, 36 and 48, there are horrible numbers with lots of factors, but I think if I just do that, and then I do I think the volume was 144.
Yes. How did you do that so quickly?
Well, I've been thinking about this problem for longer than everybody else, but while people are sharing examples in the chat and working on each other's examples, you might like to think about, is there a general strategy that you can come up with that will allow you to do what I just did and find the volume super quickly? So DS, who is initials rather than a name, so I can't say your name, I'm afraid, has put an example in the chat, 40, 56 and 35. So I'm going to have a go at that one now. Everybody else, post some examples in the chat for us to work on, and we'll see if we can come up with a general way of doing it. I think maybe give everybody, what, about 4 or 5 minutes to explore the problem?
Yes, and we're happy for everyone to post their solutions. So some people will be working on DS's, and some on Maria Luz Garrido Ruiz's, and someone Thomas Piggott's been awful.
I'm good.
1.5, 3 3/4.
At least they're small numbers.
I
think my quick method will still work.
I think that's a job for you.
Yeah. I need to see if it's possible for me to send a secret message to Thomas so I can check my answer without spoiling it for everyone else. So if you think you've worked out the volume of one of the ones that's been posted in the chat, I think you can reply to a message in the chat with what you think the volume is, and then hopefully the person who posted it will see the reply and confirm it. So I'm going to answer Thomas's now.
Alison,
yes,
I've answered the 12, 14, 42 question.
okay.
And I've posted it to everybody. Is that
No, that's fine. Yes.
Because then others can check that I've got this right.
Yeah.
And
but hopefully Maria will see your message and tell you if you're right or not.
oh, good. Not everybody has posted a question yet. We're hoping everybody will imagine a cuboid.
Yeah. But if you've imagined one of your own and you're just trying to think about how you would do the generalization, then that's okay.
Here comes another one. And I don't think we haven't worked out DS's, have we?
No, that first one, 40, 56, and 35. Ah, that's got some nice numbers in.
We're very lucky today, Alison. We seem to be working with lots of very nice people.
Who are giving nice numbers, you mean?
No, a lot of people are saying that they're nice.
Oh, right, okay. So people who posted challenges in the chat, do have a look through to see if anyone has replied to your message, and just check their answer. That would be lovely. And I think I'm going to give everybody a couple more minutes on this, and then we can start talking about strategies and generalization.
I'm just wondering, Alison, do you want me to post the one that appears on the Enrich website? Or should I leave that for later?
Let's give everything another moment.
Did you work out Thomas's problem, Alison?
Yeah, well, we could use Thomas's as an example, because we can, I think it is harder than the rest because it's moved away from using whole numbers, and so that gives us a lot more to think about if we're using a factors method. So maybe that's a good opportunity to look at the example on the Enrich website as well. So I'm just going to post the link to that in the chat, and there we are. So that's in the chat, and I'm also going to share my screen just to show the problem that inspired this. So a little bit of story time first of all. Then, when we started planning this three-dimensional thinking, we looked at problems that are already on the Enrich mapping documents and that already have teachers' notes and so on. But I stumbled across this problem when I was looking for something else entirely, and I had never seen it before, despite the fact that from the 11 years for 2009 to 2020, I was working pretty much full-time for Enrich. And I'd never come across this problem before, and I thought it was really interesting. But as you might be able to see, it is given a challenge level of 3 stars, which means that it is considered to be one of the hardest problems for that particular age 11 to 14 age group. And so Charlie and I had a chat about this, and we thought, what might we do if we wanted to use this problem in the classroom, but with a wider variety of students? And we decided that this idea of generating student examples, starting with whole numbers and thinking about how you might work out the volumes and surface areas for particular examples before moving on to some more general thinking might give people a way into this problem. And the problem that you get if you start trying to solve this one using a factors approach is that 12 can be made in lots of different ways using whole numbers. 3 can't be made with very many, but then if you start to say, well, 3 and 12 both have a factor of 3, then this would be 3 by 1, but then that would have to be 1 by 25, which doesn't work for the 12. And you soon get yourself tied up in knots. And the second part of this question, the areas of the faces of a cuboid are P, Q, and R, work out the volume in terms of P, Q, and R, gives a little bit of insight into one method that you can use in order to solve not just this problem, but all problems like it. So what I'm going to do is I'm going to switch to sharing a whiteboard so that I can do a little bit of sketching and annotation. And what I want to do is, instead of thinking about a specific cuboid, I want to think of this idea of the general cuboid with faces P, Q, and R. And ultimately, I want to know the volume of this cuboid. And so I'm also going to say, well, let's have lengths X, Y, and Z. So from this, then, I can write down some equations with X, Y, and Z in. So I can say that P is going to be X times Z. Q is going to be, this is where my visualization struggles come in, because I'm like, which length goes with which side? Q is X by Y, isn't it? And yes. Then R is Y by Z. And what I want to work out is the volume, which is X times Y times Z. So I'm going to let that just sit there for a moment. And I'm going to invite people to think about how they could work out the volume in terms of P, Q, and R instead of X, Y, and Z. Okay, so when I first started trying to work out a general way of thinking about it, and I'd set this up with the P, Q, R, X, Y, and Z, I started trying to do things with eliminating things. So using each equation to try and write one thing in terms of another. And I spotted that X times Y times Z was the same as Q times Z. And then I was like, well, can I find a way to write Z on its own? And I got myself all tied up in knots. And then I gave this problem to somebody cleverer than me. And they said straight away, well, why don't you just multiply together P, Q, and R? And I said, well, how's that going to help? And then I did it. So if you work out P, Q, R, then you get X, Z, X, Y, Y, Z, which is X squared, Y squared, Z squared, which is X, Y, Z, all squared. So that means that the volume is just the square root of PQR, which is just such a lovely result. And when I figured out that that's what it was, I just thought that was lovely. But now that we have that, that allows us to go back to Thomas's example, which I'm just scrolling up in the chat to find it. So Thomas gave us P equals 2.5, Q equals 1.5, and R equals 3.75. So instead of having to try and figure out a pair of numbers that multiplies to give 2.5, a pair of numbers that multiplies to give 1.5, and a pair of numbers that multiplies to give 3.75, such that you've got three numbers X, Y, and Z, we can just bang it into our formula now and just do the square root of 2.5 times 1.5 times 3.75. And if you do that, what you get out as your answer is 3.75. And that's why when I was trying to do it, I said, oh, maybe Thomas has been nice after all, because if the volume is 3.75 and also one of the areas is 3.75, that means that one of his dimensions must be 1. So that means that our dimensions are 1, 2.5 and 1.5. So it's not nearly as horrible as I thought it was when I first looked at the number. But this then is, I think, an interesting problem for a couple of reasons. First of all, because quite often when we're looking for a general formula for something, the way into the generalization is to do lots and lots of examples and look for patterns. But I guess that might help a little bit, but the sort of examples you generate tend to be ones where you're using common factors to help you to find it. So I think you actually need a step of insight to say, well, can I represent things algebraically? And then can I use the algebra to help with the generalization? So it's a different sort of generalization problem than others. But then it also gives you this realization that because you've worked out the volume, but you've got a cuboid and you've got the 3 areas, that automatically gives us the same lengths, because you just do V over P to give you one of the lengths, V over Q to give you the second length, and then V over R to give you the third length. So if I tell you the 3 areas of 3 faces of the cuboid, not only can
wait, Alison,
yeah,
do you mean V divided by PQ and V divided by?
No, because P is the area.
Oh, sorry.
So V over P is
Yes.
giving you, in this case, Y.
Sorry.
V over Q is giving you Z, and V over R is giving you X, presumably.
Sorry, I had your drawing covered up by my chat.
Ah, okay.
And I was thinking of PQ and R as
the lengths rather than the areas. Yeah, so that's the thing. So I was quite surprised that if you specify P, Q, and R, that is then uniquely specifying the cuboid, because the volume has to be the product of the 3 and then square rooted. And then as soon as you've got the volume, then you can work out the 3 lengths by dividing by each of the areas. So there's a lot of thinking going on that's reinforcing different bits of understanding, because we're using the volume of a cuboid, but also I think by thinking of the cuboid as being a rectangle times a length, we're thinking about prisms, and you're thinking about a cuboid as being a prism with rectangular faces in each dimension. And so I really enjoyed working on this problem as something to help me with my visualization. And I felt that my understanding of cuboids improved by thinking about it. What else do we want to say about this one, do you think, Charlie?
Can I just check I've understood what you're saying about this, the generalizing being different? The way that I've understood what you said is that often we generalize because we try some particular example, we gather some data, we have a collection of results, and often we see patterns and we conjecture from those patterns, and then we use that to come up with a generalization. In this case, spotting this general rule from the kind of surface areas that we've been given and the volumes that we've been getting is much, much harder. And that the way that this problem has been written on, appears on Enrich, is by giving a cuboid where the edges are not whole numbers, and then also suggesting that there's going to be a formula later on, it encourages students to think algebraically, because a numerical way is going to be hard and not very accessible.
Yeah, and I think you could solve it numerically, but you'd have to do a lot of trial and improvement. And the suggestion that there is a formula provokes the need to do some algebraic thinking. And I think I'm always in favor of anything that provokes a need for algebraic thinking, because one of the most common things that I hear students say to me who are anxious about maths and who dislike algebra is that they don't understand why algebra is useful. They don't understand what the point of algebra is. And I think that a problem like this, where it's quite difficult to work out without algebra, but then once you've done some generalization, you can solve a whole class of problems. So, you know, I could give you I could be thinking of any cuboid now with really horrible numbers in, but because you know that if I give you the 3 areas, you can find the product of the area and then square root it to find the volume, it's no longer a problem. It's no longer a challenge. And I like that moment when a child sees how powerful algebra can be in that way.
Good.
Have you got another problem for us, Charlie?
I'm going to share my screen.
Okay.
And let me just check. Hopefully this will work. Can you see a problem called changing areas, changing volume?
I can. I'm going to put a link to it in the chat so that people can have a look at it themselves if they'd like to.
Okay, and like Alison said, I will be sending an email, or Ellie from PTI will be forwarding an email on behalf of Alison and myself with the links to all the problems that we've been introducing and that we've been talking about. So don't panic if you're worried about where to find these. Okay, so in this problem, Alison, and I'm going to get you to talk us through how you'd approach this. We're given the dimensions of 9 cuboids. And the idea is to arrange them into a 3x3 grid, which looks like the one below. And as it says here, as you go from left to right, the surface area of the shapes increases. As you go from top to bottom, the volume of the shapes must increase. All the cuboids in the middle column will have the same surface area. All the cuboids in the middle row will have the same volume. So I've prepared a table for you, and I'm going to share. Let's have a look. Good. Where is this? Here we are. So I've got all 9 cards here for you. And the idea is you're going to have to figure out. So I don't know how you want me to lay this out, Alison.
Well, the first thing I'm thinking is this is like my worst nightmare, because these things are written in words, 2x4x6 or 1x2x28. I have no idea what any of these things look like, and so I think I want to start by thinking about what each of these looks like. And I think if I was a student, I might want to be working in a group on this. I might not want to be working on my own, because I might want to be able to discuss my reasoning with other people. So I think I'm going to be asking for quite a lot of help from the chat for this. So you said that 3 of them had the same volume, is that right? Or at least 3 of them have the same volume that are going to go in the middle. Some of them have a smaller volume and some have the larger volume.
Yes.
So maybe I'll start by thinking about the volume then, and finding some that have smaller volumes, some that have larger volumes, and then think about the surface area. So I think I actually want you to move the grid to the side and out of the way, because I don't think I'm ready to start thinking about the grid yet. I just want to sort of see the individual cards, if that's okay. And so I'm imagining I might want to invite students to justify statements that they can make about these. So I'm going to start up. Can you just move it down slightly, because the very top one has disappeared off my screen. That's lovely. Thank you. Do
you want me to write some volumes down on some of the cards?
You could do, although to be honest right now, I'm more interested in whether a volume is just bigger or smaller. So for example, I've seen a 2x4x6 and a 2x4x7. I know that the volume of the 2x4x7 is definitely more than the 2x4x6. So wherever they go in the grid, the 2x4x7 is going to go below. And in fact, I think I can justify that the surface area of the 2x4x7 is bigger as well. So not only is it going to be below, it's going to be to the right. And so my justification for that is that they've both got a face that is 2x4. So I'm imagining that extruding itself outwards, but the 2x4x7 has extruded out a little bit more. So it's got like an extra ring of area over the 2x4x6. So I don't know whereabouts they go in the grid, but I do know that that one is to the southeast of that one. So what I think I'm going to do is I'm going to do a little bit of buying myself some time by doing some thinking and just looking at what I've got. But I'm going to invite everybody else to do the same and to have a look at the cards that are available and see if they can come up with a similar description where they say, I know this has a greater volume because, or I know this has a greater surface area because. So I'm going to do a little bit of thinking. I'm going to shut up for a moment. And we also know that some have the same volume and the same surface area, don't we? So if anybody can see 2 that have the same volume and have an argument for that, then that would be good too. So I'm going to shut up for a moment. I'm going to give everybody a chance to look and to think. And if anyone's spotted something that they think will help me, either type your answer in the chat, or if you want to unmute and just tell me, that's fine as well. The 1x2x24 and the 1x2x26. I think I can do a similar argument that the 1x2x26 must have a greater volume and a greater surface area. So I don't know how it relates to the 2 I've already got, but I know that they're in that same sort of, one is diagonal from the other. Yeah.
I think this one that I've got here can be connected to the others that are, well, you've got 4x7 there and you've got 4x7 here. And this is 5x4x7 and this is 2x4x7. I think you can use a similar argument for those.
So that means that that's got to be the main diagonal of the grid above. So if you move the grid down.
Well, perhaps, but I've also got 1x2x28 here. I've got 1x2x24, 1x2x26, 1x2x28. So.
Oh, yeah. Okay.
So I'm not sure.
I think I need to find something that's got the same volume as something else. Can anyone spot two that have the same volume?
I'll go writing at the bottom of the cards. Can you see that?
Yeah.
I'm doing the easy ones first.
The feeling you might. Okay, DS says that 2x4x7 and 1x14x4 have the same volume. Do you want to either type in the chat, or you can unmute yourself if that's easier, and just tell me your reasoning for those two having the same volume?
Sure, because it's 2x4x7 and 14 you can split up into 2 and 7. So it's 2x7x4, 2x4x7.
Okay, so you've sort of done a halving one and doubling the other trick. So I could picture that by imagining my 1x4x14 cuboid and cutting the 14 in half to give me 2 7s, and then sort of stacking my cuboid to make the 2x4x7. That's
same
lovely.
with the 1x2x28, same volume.
Okay, so yeah, I can split the 1x4x14 into 1x2x14 and have 2 of those, and then put them together to make a 1x2x28. That's lovely. So this is the sort of justification that means that although Charlie is writing that they all have a volume of 56, we don't even need to know that that volume is 56 to be able to give a mathematical reason why all 3 of those have the same volume.
So can I just check? I did this last one, picturing the one above it being sliced in half, the 4 length becoming 2, and then that the 2 halves being put side by side, so 2 14s making 28.
Yeah, I've realized something interesting, which is that in my head, I'm making these cuboids out of marzipan and then cutting them and then reassembling them. And I don't know why my brain has decided that marzipan is the substance that I'm using, but I just thought I would share that with everybody.
Earlier, Alison, we talked about how, well, perhaps we didn't, but I know that for a given volume, you can minimize the surface area by making cuboids as close to a cube as possible. So in the same spirit that you're saying, well, perhaps there was no need to write the volume, we could picture a 2x4x7 as being more cube-like than a 1x4x14, which is a bit more cube-like than the 1x2x28. So my conjecture is that the surface area of the bottom one will be greater. So I'm conjecturing, I'm going to move these out of the way for a minute.
That the surface areas in the 3 that you've put in there are going from smallest to biggest. And I think I agree with you because of the marzipan that I'm thinking about. Because if I have a 2x4x7 cuboid, and then I take the bit that is 2 centimeters, so I've got 2x4x7, I'm picturing that in my mind now, and I slice through and then separate it out to make a 1x4x14, I'm losing a little bit of surface area where I connect those edges together to make my new cuboid, but I'm gaining a much bigger surface area where I've made the cut. So when I cut them and reassemble them, I can think about how much extra I gain versus how much I lose when I push them back together again. and use that to convince myself of the increasing surface area. I am going to have to work out some surface areas at some point though, aren't I? Because I need to work out the ones that have equal surface area to each other. And I don't think I've got any good intuitive ways of thinking about that. I know that 4x5x7 and 4x5x6 both, and it in fact, 2x4x6. Yeah, I like that. I'm going to have to work out some surface areas, but I don't need to work out the whole surface area, do I? I could just work out half of the surface area. So I can do 1 times 4 and 1 times 14 and 4 times 14 and add that up and then double it, and that will give me the surface area. I'm going to use a calculator. Is that all right?
We'll allow you a calculator.
Plus 1 times 14 plus 4 times 14 times 2. So I think the one in the very middle, the 1x4x14, I think it has surface area 148.
Yes, I agree. I mean, you could just work with half surface areas.
And I've just checked, and the 4x5x6 also has a surface area of 148, so that can go directly below the one that's in the middle, because it has the same surface area, but it has a bigger volume because it is more cube-like. Which means then that the 4x5x7 must go in the bottom right because it's got a bigger surface area and a bigger volume. So yes.
So just tell me again why you knew that the 4x5x6 went below the 1x4x14.
Because a very wise man told me that if it was more like a cube, that it had a bigger volume. And I know it has the same surface area as the one above, but it is more cube-like, so I put it below.
So you're saying the volume is 56 plus, and we don't need to know what it is.
Yeah.
But because it's more cube-like for the same surface area,
yeah,
we can guarantee that. That's nice reasoning.
So what
and
else?
Can I just check for the 4x5x7? You've compared it with the one to the left, so we know that the surface area is going to be more than 148.
Yeah, and we know that it's got a bigger volume than the one above, because it's got a bigger volume than the one to the left of it. So it must also have a, because they've all got the same volume.
So the volume is going to be, again, 56 plus.
More than 56, because it's got a volume more than the one. Yes, good. A 4x4x4 cube, that's going to be really easy to work out the surface area of, because it's going to be 16 times 6, which is,
which one are you looking at?
The 4x4x4 cube.
Sorry, yes.
So the volume is going to be 64 because it's 4 times 4 times 4, and the surface area is going to be 96 because it's 4x4 times by 6 faces. So it's got a bigger volume than the middle row, so it needs to go on the bottom row. but it's got a smaller surface area than the other ones in that row. So it goes in the bottom left. The
Do you need to convince yourself that this has got a smaller surface area than the one above?
I don't need to know how its surface area compares with the one above.
Because you're just comparing volume. I'm sorry. Yes.
Yeah. The 2x4x6 has to go above the 2x4x7. I think.
Because the volume is going to be less than 56.
That's a very good point, Thomas. I think a lot of students would want to work this out by just working out all of the volumes and all of the surface areas and arranging them on the grid. But, you know, I'm absolutely fine with that, because that turns it into a purposeful practice activity where over the course of the academic year, I want them to do some practice in finding volumes and surface areas. And if I get them to solve it, to practice that during some problem solving, then not only are they getting the benefits of the practice, but also they're getting the benefits of the problem solving and the doing some collaborative working. So what might happen is they might just do what Charlie's doing and write down the volume and the surface area on all of the cards and then arrange them. And then I might go around and ask them and say, could you have worked out that this card went to the left of this one or this card went to the right of this one without actually having to calculate it? And so then for a lot of students, they might do it the other way around from how I have, and do the calculating first and then the reasoning and developing intuition part of it second. Now, I don't know whereabouts that one that I've just put in the top left. Am I sure it goes in the top left? I know it has a smaller volume than the ones that are already there, but I don't know how its surface area compares with the two. So I think I need to take that out and just double check that.
We know that these two are very similar.
That way around, yeah.
And it's just whether, I suppose,
whether they go to the left or to the right.
Whether they go like that, or like that.
Yeah. So figuring out which of them has the same surface area as the one below might help. But again, this is a nice thing where I can imagine if you're working in a group, different students in the group could work on different things to split the work up.
Well, if we worked out the volume of this one, which is quite easy to do, it's 48, then these two have got the same volume. And this one is much more cube-like. So this will have a
smaller surface area.
So I think if we change the 56 minus to 48 exactly, then we've got the right order, because we know that this has got a larger surface area than that. These two have got the same volume, and this is more cube-like, so this will have a smaller surface area than that. So that must be the right order.
And of course, if you specifically wanted students to have to work out the volume and the surface area, then what you could do is you could put in some red herrings where things, you know, fitted in between, or where there was an option for what to put somewhere, so that they can't use the structure of the task because I was saying things like, I know I have to look for 3 volumes that are the same to go across the middle. But if I also had, you know, some other things in there that had the same volume, then maybe I would have to choose to make some better choices that way. So yes, Thomas, I think your question is an excellent question, and I hope I've managed to convince you that if students wanted to approach it using the intuition method that I did, then afterwards as a teacher you can say, well, okay, but I want you to work out the surface areas and volumes just to demonstrate that your intuition hasn't broken anywhere. And then if, as I suspect is more likely, students are just going to want to work them all out and then arrange them in the grid, that's giving them the opportunity to do the practice. But then also you can pose the question, could you have worked out which way around these 2 cards went without having to do the calculation? And so then that's doing the building intuition bit.
I think I'm going to stop sharing this and just very quickly share the rest of the problem.
Okay.
Which I hope you can see that, which says, once you've placed the 9 cards, take a look at the extended grid below and see whether you can find what you could place in the other 4 empty squares.
And I think in order to do that, you really do have to start thinking about how the dimensions, how the volume and the surface area change as you change the dimensions, because you have to understand the structure of what's going on to be able to go out. We are very close to running out of time, and we haven't talked about 3D treasure hunt yet. Can I very quickly I'll pop the link in the chat.
I've got it on my screen.
Okay.
Right now, I seem to have a level 1 problem.
That's because you've gone to treasure hunt rather than 3D treasure hunt, Charlie.
I'm going to go to level 4, which I'm presuming is going to be the 3D treasure hunt.
If you go to the link that I've just posted in the chat, it should take you straight to 3D treasure hunt.
Okay.
With the 3D version. Okay, so we wanted to show this one. We haven't got a lot of time to discuss it, but this might be one to go away and have a play with. So 3-dimensional coordinates, we don't do masses on in Key Stage 3 and Key Stage 4. It becomes more important to think about in Key Stage 5, particularly when thinking about vectors in 3 dimensions. And I think because there's quite a lot of nice coordinate-based thinking that goes on with this problem, even though it might not be quite so firmly anchored to the curriculum, the strategic thinking in it is just brilliant. And it's also the sort of thing that if you show it to some keen kids, they will go away and want to find a strategy. And I think that's kind of what we're hoping will happen with you, that we'll show you the idea of the problem and that you'll want to go away and have a go at it and find a strategy for yourself. But yeah, just to show the interactivity and what's happening with it, there is some treasure hidden somewhere in that grid, and it is a 9 by 9 by 9 grid. So you've got 10 values from 0 to 9 that can represent each thing. So there's actually 1,000 places that the treasure could be hidden. And we have to try and narrow it down as quickly as possible. So can you just put in the coordinate 0, 0, 0, Charlie, just so that we can see what happens? Because I might decide, well, I'm just going to start in the bottom corner, and it tells me that I'm only 19 steps away from the treasure, but that could be going 6 in the X direction and then 9 in the Y direction and then 4 in the Z direction. Or it could be, well, basically any combination that adds up to 19 steps. So that hasn't actually narrowed it down that much. But I could then put in a second guess. I might guess 900. I might think that picking corners to try and narrow down to the middle would be a good idea. And then it tells me that it's 12 steps away. So by careful choice of subsequent guess, I'm getting more and more clues until eventually I can find the hidden treasure. And I think, Charlie, this is always possible in, is it in less than 5 guesses?
Yes, with the right strategy. Let me just see, if I type in a third one here, then I think
don't put too much in, because you might give away what your strategy is.
No, but I think I can work out where the treasure is on my 4th go.
Okay, so there is more than one different strategy. Charlie and I had a massive fight about this the other day, about what was the best strategy, because his strategy makes absolutely no sense to me and my strategy makes absolutely no sense to him. But there is a 2-dimensional version of this task, and what I like is that by moving to 3 dimensions, you then open up a whole different set of thoughts about it. We are right up against the end of time, and I know a couple of people have already said that they have to go, so I don't want to keep anybody behind. But all of the problems that we've shared today you can find by looking on the secondary teachers page, and then either going to browsing these secondary curriculum areas. They're all in geometry and measure, either 3D shapes or perimeter area and volume, or you can go to the full mapping document and find the problems linked there. But as Charlie said a couple of times, we are going to put an email together with links to all of the things that we've shared, so that you can access them and browse them. And if you want to get in touch with either of us to share any strategies that you've come up with, or any frustration that you can't find a strategy for the 3D treasure hunt, then we'll include ways of contacting us both as well. But yeah, really hope that that's been useful to everyone, and that you've had the opportunity to reflect on how 3-dimensional thinking is something that, yeah, some students find it difficult, but by providing opportunities for discussion and hands-on resources to use to help to build those intuitions, that it can become something that can actually be a little bit of a favorite topic to work on and teach.
Well, and like you say, Alison, sometimes we see things in different ways, so it really does lend itself for students explaining and justifying and discussing different ways in a way that sometimes other topics don't. So we will send you the links to all the problems, and I might include one extra one that we didn't get a chance to do that is one of our favorites.